can see my screen. Can you guys see my screen?
Yes, we can.
Okay. Now, as we are not so many, if you feel that you have got any questions, please just unmute yourself and stop me and ask the question so that you don't get left behind. Warm welcome to our first lesson. My name is Namadzabo Kone, and today we are going to deal with two topics in Unit 3 and Unit 4. Unit 3 is about trigonometric integrals, and Unit 4 is about integrals of hyperbolic functions. Firstly, before we get onto the integration itself, there are two rules that are very important in integration. Whether you are doing integration of normal functions, whether it's hyperbolic functions, whether it's trigonometric functions, you will find that these two rules will apply all the time. So it does not always mean that when you see a trigonometric function in an integral, that you will go and look straight for the answer in the information sheet. And can I please request you to just make sure that you have got access to your information sheet so that you can be able to refer to these rules as we go on with our lesson. I was saying that when you see a trigonometric function or a hyperbolic function in an integral, it does not always mean that you will have to go straight into the information sheet and look for the solution of that. There should be maybe some ways in which you can recreate the given function so that it looks like either rule number 2 or rule number 3. That is why I'm starting by having a look at these two rules, because you will see that they will always all the time they will get involved, even if when we are dealing with trigonometry and hyperbolic functions. The first rule, which I consider as the one of the most important rules of integration, is the one that you can see on the screen here. It says the integral of f of x to the power n multiplied by the derivative of the function of x dx. Now, let me just first explain the meaning of what you see on the left-hand side. This sign, the integral sign, has got no meaning if it does not have that dx. This dx tells us the variable with which we are doing integration. If it is not there, then the integral has no meaning. Because if I can change this dx now to a dy, for example, then it means that whatever you see before the dy will be constant if they are in terms of x and there is no y. So that dx is very, very important. So it tells us that we are doing integration with respect to the variable x. Now, if you look at integration is just the reverse of differentiation. If we can start from the right side and we do differentiation on what we are given on the right-hand side of this equation, if you've got a function of x raised to the power of n plus 1 and you want to do a derivative, what you normally do is you take this n plus 1 and you multiply it in front. When you multiply the n plus 1 in front, it will divide this other n plus 1 that is there on the right side, and then you will remain with f of x to the power of n plus 1. Then on the n plus 1, you subtract 1. What remains now will be f to the power of x to the power n. Now, if you are doing the power of function rule of differentiation, when you are done with this thing of taking the n plus 1 to the left and subtract 1, you have to multiply by the derivative of what is inside. Now, that is where this red derivative here on the left-hand side is coming from. So now that we are doing the reverse of differentiation, this derivative in red that you see here must just stand there for the process of integration to happen. Because if this derivative is not here and there is a function of x raised to an exponent, you cannot do what we are doing on the right-hand side. Now, what we are doing on the right-hand side is to take this function of x and take its n, which is the exponent. You add 1 to the exponent and divide by the result. And then you add c, which is a constant. I think from your previous course, Maths 1, and then your first units, you have done already integration of basic functions. So then this integral happens only when n is not equal to minus 1. Because if we can do the same integration with n equals to minus 1, what will happen there on top will be minus 1 plus 1, which is 0. And here at the bottom again, minus 1 plus 1, which is 0. And you all know that we cannot divide by a 0. So that is why we have to restrict that n must never be equal to 1. Now, if where we get n equals to minus 1, then the rule number 3 applies. Rule number 3 is exactly the same as rule number 2, in the sense that the only difference is that our n in this case is negative 1. That is why you see your fx here at the bottom. If you take this f of x up, it becomes f of x to the power of minus 1. And hence, we cannot do the same as we did in rule number 2. We are supposed to now come up with ln of the function f of x plus c. And you can easily check that this integral is correct, because if you are asked to find the derivative of ln of f of x, what you do is you first find the derivative of f of x and you divide by f of x as it is, which is what you see here. But now this in red here is the derivative of the function f of x. It just sits there for this process to happen. You don't see it on the right-hand side. That is why I've put it in red in both the two equations. And also, as we deal with our integrals today, wherever we will need this derivative, I will also put it in red so that you can see that it must just sit there to induce us to be able to apply these rules when we have to use these rules. Now we'll start with our first example. I just tried and picked examples of different types so that I can be able to use them to explain to you what are the do's and the don'ts, and what are the things that you should look out for. Now, say if this was the integral of cos x dx without the power 5, then, as I have said at the beginning, you will just go straight to the information sheet and look for the integral, and you find the answer and you write it down, and that's it. But now that it has got a power 5, there are some things that you need to do, because there is no integrals of powers of trigonometric functions except two, which are sec squared and cosec squared. The two integrals are the only ones that you can go and find in the information sheet. The other trigonometric functions with powers that are more than one, you are supposed to do something, work out something to make it easier for you to be able to do the integration, like the example we have here. Now, there are two possibilities. One possibility is the one that we have where the power is odd. That is the power that cannot be divided by 2. Then in the next example, you will see when we deal with a power that is even, how you have to deal with it. Now, let's start by explaining when the power is odd. Now, when the power is odd, you have to release just one trigonometric function outside the power that we have. So which means that we are supposed to now first rewrite this cos to the power of 5, this cos of x to the power of 5. We have to now first rewrite it as follows. We take the cos x, the single one, and we release it and we put it next to the dx. Then the rest that is remaining will be cos to the power of 4x. Now, because power of 4 has no identities that we know, I rewrote it as cos squared x, again power of 2, which brings me back to the cos to the power of 4, and then times this cos of x that is outside will bring us back to the original, which is cos to the power of 5x. So this that I have just shown you now is the same thing that we were given. It's just that the causes are separated now in terms of powers. We have isolated one cos of x, and then the other cos to the power of 4, I have just rewrote it as cos squared and then another bracket squared outside, which still means give us the cos to the power of 4x. Now, the reason why I did this is for us to be able to go and apply our squared identities. Because you will remember that there are squared identities that we can be able to do to change this cos squared. And we do it like I'm showing it you here. We replace now the cos squared x by 1 minus sine squared x, because we know that cos squared x plus sine squared x is equals to 1. So if we make cos squared x the subject of the formula, then we get our cos squared x equivalent to 1 minus sine squared x. Then what we just did here is to replace the cos squared x inside the bracket. But now this 1 minus sine squared x is squared. So we need to now use our basic algebra and we square this bracket. When we square this bracket, a lot of people make the following mistakes, which you have to bear in mind. You cannot come in here and say this is the same as 1 squared minus sine to the power of 4x. You can't do that because this is a binomial. You are supposed to take 1 and it must multiply the whole bracket 1 minus sine squared x, and you take minus sine squared, it must multiply the whole bracket 1 minus sine squared x. So that in the end, you get an expression that looks like that. This is what, after we have expanded 1 minus sine squared x squared. Now, we have got now 3 terms inside the bracket, and they are all multiplied by cos x dx. So we will take this cos x dx and multiply it inside the bracket. So it has to multiply each one of the terms that are inside the bracket. When we do that, we eventually have the one that multiplies cos x dx, which gives us the first term, which is this one, cos x dx. Then the middle term multiplies cos x dx. What I just did was to factor out the 2, because 2 is a constant, it's a number. It has nothing to do with the x, which is the variable that we are doing integration with. So you are allowed to move in and outside a constant number without changing anything. So that is what I did here. And you can see now my cos x is in red. As I have said, that when we are supposed to need that rule that I have shown you at the beginning, I will always put the derivative that just has to sit there in red, so that you can see that our integral is rule number 2 or rule number 3. Then you will realize that the first term, it will be the one that you can go straight to the information sheet and you look for the integral thereof. Then the last term is that sine to the power of 4x multiplied by cos x dx. And again here, we put the cos x in red just for you to be able to see that that is standing there as the derivative. Now, the rule that we are going to use for the first term, if you go to your information sheet, you will realize that it is rule number 7. If you go to rule number 7, it has got an integral of a cos function, and it gives you that the integral it's a sine of x. Then when we come to the next 2 terms, now we know that the derivative of sine is cos. The derivative of normal sine is cos. Now the power 2 that you see here is that value of n that we talked about in the function of x itself. So what you look at is the derivative of the trigonometric function without including the exponent. So you ask yourself, what is the derivative of sine of x? And then you will go there and you find that it is cos of x. That is why it is in red here. So that now this sine of x behaves like rule number 2 with it behaves like f of x in rule number 2. So our n is 2 in the middle term. In the last term, the same applies. Our n is 4. So sine of x is your f of x. Its derivative is cos x, is sitting there. So that when you do the integral, you end up having something like this. How did we get these individual terms? The first one, it's straightforward from the information booklet. The integral of cos x dx is sine x, which is the first term here. And in the second one now, Because now sine of x is f of x. For you to be able to do its integration, it needs its derivative, which is sitting here. So you take the exponent, which is 3, you add 1, and you get this power of 3. Then after that, you divide by the result, which is your n plus 1, which is this 3. So that is why you have got now your minus 2 over 3 here, and your sine to the power of 3x. That 3 is coming from that first formula that we did, which says you take f of x and you've got your n, you add 1 to n, and you divide by the result. And we did exactly the same with the last term, which is this one. We took the 4, we added 1, and we divide by the result. 4 plus 1 is 5, and you divide by 5, which is this 1 over 5 that you see here, and then you get a plus c. And that will bring us to the end of this question. You can see that although it looks like a very small question, cos to the power of 5x dx, it needs a little bit of more arithmetic for you to be able to reach to the final answer. There's no way in which you can go and look for this integral straight in the information sheet, because the information sheet has got only the integrals of basic names: cos, tan, sine, cosec, cot, and so on. But only those two that I've mentioned, sec squared and cosec squared, they do have direct integrals that you can read from the information sheet. Now we can move to the next question. As I said, I will now move to a question that contains an even power. Now, when the power is even, we cannot take one sine of x out like we did before. Because if we take one sine of x out, we are going to be left with a power of 3. And then when we have got a power of 3, we will be stuck, because there are no identities that involves power of 3 that we deal with. We deal with powers of 2. So instead of taking out one sine of x here, what we will do is we will rewrite this as a power of 2. Like we did in the previous example, wherever we had a power of 4, we wrote it as a power of 2, which means that if this if this even power was power 6, for example, we would have sine squared inside the bracket and a power of 3 outside. If it was power 8, it would be sine squared x and power 4 outside, and so on. If the power is odd, then you just factor out one of the power one sine of x, and whatever you are left with will be an even power, and then you do what we are doing currently now with that even power. So then now, when we've got sine squared of x, it is still only one name here, but inside it has got a power 2, and there is no direct integral as well that we can use. Now we will have to go and check now our identities in compound angles. There are identities in compound angles that can help us to reduce a power of 2 into a trigonometric function of power 1. And that trigonometric identity looks like that. If you can go to your information sheet, you will find this identity. It says if you have got sine squared a, you can rewrite it as 1 over 2 into 1 minus cos 2a. Where do we find it? Where did they establish this identity from? If you can remember compound angles, when you have got compound the cos of 2a, when you expand cos of 2a, you can expand it as cos squared a minus sine squared a. And if you can change that cos squared a into 1 minus sine squared a, then you will have cos 2a equals to 1 minus 2 sine squared a. If you can make sine squared a the subject of the formula, you get this formula that is in here. But luckily they did it for you, so it's there in your information booklet. You just go there and look for it and find it and come and use it in your integral. Now, if you can check, wherever ax is sitting here, there's an a sitting there. And on the right side now, it becomes a 2a. So which means that in our case, on the left-hand side, it will also become a 2x. That is why now your expression will become like that, applying that rule that is on the far right there. So it becomes now the integral of 1 over 2, 1 minus cos of 2x. All of this is still squared. You don't have to forget the square. Now, what do we do with the square? We also do the binomial expansion here and multiply this. Not that this power 2 comes to half, comes to 1, and comes to cos 2x like a lot of people do, because that is wrong. You have to expand it properly and have it as you see on the screen now. So the 1 over 4 is when we have 1 over 2 squared. Now, because 1 over 4 is just a number, it does not contain x, I decided to put it outside the integral sign. But don't forget that with this 1 over 4 applies to all of these values that are in here when we are done with the integration. So this 1 over 4 must come to each one of those three terms. Now, the first term it's only 1, which is this one. And then the middle term, after you multiply this and that, multiply this and that, and you add like terms, you get this one. And then the last term is cos squared 2x. Now, this is a problem because cos squared does not have an integral. So we need to also get rid of the power 2 here. And we will go back to trigonometry, compound angles, and check the formulas, and we will find this formula that can help us to remove the cos squared x. But now when we check our angles, here is angle A, and here is the angle now, which is 2x. So when we remove this power 2 using this rule, the angle A must be doubled if you check on the right side. So which means that also here, when we bring in the right-hand side of that rule of cosine squared A, we will have to double this angle 2x. So that we get a step that looks like that. Now, what I just did was to just separate these integrals. The first one on the far left is this 1 over 4, an integral of 1 dx. So what I did, I just multiplied the dx with the 1 to get this first integral of 1 dx. We just don't write the 1 because 1 times any number, the answer is that number. Then the second term is everything that you see there. It's everything, sorry, I pressed wrong button. It's everything that you see there, and then the 1 over 4 comes and applies on the integral as well. Then the last term is the plus cos squared 2x, which has now been transformed to this 1 plus cos 4x. So then they apply the integral. The 1 over 4 comes with it, and the integral is that 1 over 2. This is just the substitution of this value with its equivalent from this rule that is there on the far right hand side. Now we need to apply the integrals on each one of the two terms that are in here. Now you can look at here. If 1 over 4 is multiplied by 1 over 2, we get 1 over 8. And it applies to this 1 dx. So we'll have 1 over 8 integral dx, and we've got also 1 over 4 integral dx. Those are like terms. And when we add 1 over 4 and 1 over 8, we get 3 over 8. That is why in the next step, you see 3 over 8 integral dx. It is from this product, 1 over 4 times 1 over 2, which is 1 over 8, and 1 over 8 plus 1 over 4, it gives us 3 over 8. That is where you get this first term from. This one is exactly the one that you see here. Now, the reason why I wrote this 2 in red is because when we go to the rule that we are supposed to find the integral of cos of f at x, you will see that the cos of f at x, it is accompanied by the derivative of f of x. And that is why we must have these 2 sitting here just to make this get its integral from that rule. Same applies to this side. But here now, we have got 1 over 8. Now this 1 over 8 sitting outside will remain 1 over 8. But here, for us to be able to do integration, we need the derivative of 4x to accompany cos 4x. That's why I must bring in this 4 and counter it by a 1 over 4. Now, that 1 over 4 multiplies. And I've made a mistake here, you can see now, because this is 1 over 8. And then there is a 4 that we bring in here, and we counter that by a 1 over 4. That 1 over 4 must multiply the 1 over 8, not the 1 over 4 only. So this was supposed to be 1 over 32, not 1 over 16. So here is my mistake. If I was doing a test or an exam, I would have got this one wrong. So please note that this 1 over 16 is supposed to be 1 over 32 because it is 1 over 8, which is this product, multiplying that one. Initially, it will be 1 over 8 cos 4x dx. And because we need the 4, we need to compensate by a 1 over 4. So it will be 1 over 8 times 1 over 4, which is 1 over 32, down here at 1 over 16. I'm so sorry about that. And now we are ready to do integration. When we integrate, we will find that the first one, because it's 1 dx, and then the integral of 1 dx is x. So that is why we put it 3 over 8. Then we go to the second one. We go to the information book and we go to look at rule number 7. Rule number 7, it will tell you that when you see the integral of cos 4x, it has to be accompanied by the derivative of 2x, which is the 2, and we get sine 2x. The 1 of minus 1 over 4 is the one that is outside. As I have said previously, this is 1 over 32, and then the integral is the same rule, which is going to be sine of 4x. So as I said, if you've got any questions, please do not hesitate to stop me and ask the question. You just unmute yourself and ask the question. Then we will move on to the next example. Now, the next example is a mixture of two different trigonometric ratios, and they both have got exponents. And you know that in the integral, there, for us to do integration that involves exponents, for this sine and cosine, there are no direct integrals that we will find there. So which means, now that we've got sine with a power of 3, it is better for us to exclude one sine x there so that we can remain with a sine with power of 2. Because what we know is that there are what we call squared identities. So which means that if this sine was power of 5, we would do exactly the same. We exclude only one sine of x and we remain with sine power of 4. And then we rewrite that sine power of 4 as sine squared, as I did in the previous example. But now, luckily for us, it is power of 3. If we can just remove one sine, then we can have something that looks like this. Now, if you can check, that sine power of 3 has been removed. It is now here close to dx. So it is sitting here, and now we've got powers of 2. Now, the next thing, this is very important. That is why I always say that for you to be able to excel in integration, you have to master your derivatives. Now, why did I say that? I am saying this because if now you have got this situation, you have got sine squared and cos squared, you need to decide which one of the two must change into the other. Then, if you know that the derivative, which is this one now, it will be acting as a derivative. This sine x is a derivative of cosine. So it means that you need both these two to be in terms of cosine. So you will never go and change this cos squared, because if you do that, then you will get stuck with something that has got both signs only with exponents, and then a sine x here dx, and then you will not have any derivative of anything. So which means that you will just go and get stuck. So for you not to get stuck, you need to understand that this must be a derivative of something that is sitting here. That's why you need to change sine squared into cos squared in the next step. And you use the identity that we have talked about before. The sine squared x plus cos squared x is equal to 1. Then you will get it looking like what you see on the screen. Then from there, it's just a matter of multiplying cos squared x sine x dx inside the bracket. And when you do that, you get something that looks like that. Now, you will realize that when you multiply 1 by cos squared x sine x dx, you get the integral of cos squared x sine x dx. But the problem is that the derivative of cos is negative sine x. That's why I have put in this negative sign x here inside, and I've put a minus sign outside. This is the same as putting -1 here and putting -1 outside. When you multiply this -1 inside, it cancels this negative, and you'll get back to this 1 times cos squared x sine x dx. Then that is why we need this negative sign in here, because the derivative of cos is minus sign. If you can go and on the information sheet. Now, we do the same with this other one. You multiply this minus cos squared x by cos squared x sine x dx, and you get cos to the power 4 x. And then I did the same thing here. There was this negative sign before, which was outside here. I remove it and put it inside so that you can sit with sine x here for it to look exactly like the derivative of cos x. That's why here now you see a plus sign there. From there, it's just a matter of going to your rules and you check rule number 2. Although here we're working with trigonometric functions, we are not going to do any integrals of trigonometric function. We are going to use that rule that I have shared with you at the beginning. Our f of x in the first term is cos x, and it's raised to the power n, which is equals to 2. And our f of x in the second integral is cos x. It is raised to the power n, which is equals to 4. Then this happens. So you come here for the first term, you add 1 and divide by the result. That's where you get this negative sign that is outside sitting here, and you get 1 over 3 cos power 3x. Second one, you add 1, divide by the result, power 5, divide, and then here you've got a 1 over 5. And then you just go and say plus c. And that's how you do this kind of a question. So now we proceed to the next example. Now we get something that has got all powers that are even. Now, when we deal with tan and secant, and when we deal with cot and cosecant, there are two things that you need to look out for. Because you know from derivatives that tan, the derivative of tan is sec squared. Then you ask yourself, is it possible for us here to have a sec squared separated from what we are given? Now that the power is 4, the answer is yes. We can have a sec squared separated and still have a sec squared remaining there, and we've got identities that can help us sort that out. Now, say for example, we had tan power 6x and sec power 5x. Then you know if you can remove sec squared here, you are going to remain with sec power of 3. Then that is a problem, because now you will have sec to the power of 3, which you will have not, you will do nothing about. So in that case, when you have a sec with power of 3, then you think about now the issue of the derivative of sec itself. You look at now sec. What is the derivative of sec? When you go and look at the information booklet, you will find that the derivative of sec is sec x tan x. So it means that it will be best for you now to pick out both tan and sec individual power 1 of tan x and sec x, and you put them separately from the rest of what you are given. But in this case, because our power of 4 is even, then we are supposed to now go and separate sec squared x, which is that derivative that we are looking for. So we do that, and we are doing it because the derivative of tan x is sec squared x. Then from there, we separate. We separate that sec power of 4 into sec squared x times sec squared x. Our aim is to have one of the sec squared as a derivative. And now that we've got it there, then it means that now we need to make the sec squared x disappear. We need to remove this sec squared x so that everything can be in terms of tangent. And that we are going to do because we have got an identity that looks like that. 1 plus tan squared x is equal to sec squared x. Then we are going to replace sec squared x onto the left-hand side, only one of them, not both, because we still need one as a derivative. So what the first one is removed so that we have something that looks like that. Then now we remove brackets and have separate integrals. And the separate integrals will look like that. The first one has got a 1 here, which will make it tan 6 power of x, staying as it is, as you see in the first integral, and we multiply by sec squared x dx, which is sitting there. And I deliberately put in sec squared in red, because that sec squared is just a derivative. Then the second one, if you can check the second term here, it is tan squared itself. So that tan, you multiply by the tan to the power of 6 first, and you get this tan to the power of 8, and then sec squared x dx come and sit down there. Then you are sorted. What you just need to do is to go to that rule that I said is very important, and you apply that rule. And so you will get the result that you see there. So you take the 6, you add 1, divide by the result, so you get that. Second one, same thing, you add 1 onto the 9, and you divide by the result. Remember, in this case, your f of x is tan x in both the two terms. And the power that you see there, you just do the powers exactly the same way as you do in that function of x raised to the power of n accompanied by its derivative. Is there a question?
Yes, sir.
Okay.
Please explain step 3 again.
Step 3, the one in red or the one before that?
The one in red.
Oh, okay. Now the one in red, do you understand where we get this 1 plus tan squared x from? From the
Yes.
identity on the right side. Now what we are doing is we are taking this tan to the power 6x and sec squared x dx and multiply it inside this bracket. So when we take tan power 6x and sec squared x dx and multiply by 1, we get the first term, which is this one. Then now again, we must take the same tan to the power 6x and sec squared x dx and multiply it with tan squared. So when we multiply tan power 6 with tan squared, we get tan power 8. Then sec squared dx still sits there as well. So that's how we got these two terms. Now from these two terms to the final answer. Now because sec squared x is the derivative of tan x. Remember, 6 is a power, it's an n. You don't consider it, it is your f of x is only tan x. Then your n is 6 in the first term. So that tan x is accompanied by its derivative. The derivative of tan x is sec squared x. If you can check that one over there. Then that is why we said, let's add 1 to the 6 and divide by the result like we do in rule number 2. And we do the same with the last term. We add 1 and divide by the result, and we get tan power 9. And then this one is 1 over 9. Does that make sense?
Yes, sir. Thank you.
Okay. All right. Now we can move to the next example. The next example now is the one that I just explained. It has got now powers that are odd. Now with these powers that are odd, there is, if we can take out sec squared theta and we say it is the derivative of tan, then what we will remain with, it will be sec power of 3 theta after we take away the sec squared. So it means here it won't work that way. So now that the power is odd, now we will have to now change and say, okay, let's consider our f of x as sec theta. And we ask ourselves, what is the derivative of sec of theta? And when you check, you find that the derivative of sec of theta is tan theta sec theta. And we've got it in that midst of all those powers there. So what we just do, we take away that which we want to separate as a derivative. So which means that from power of 3 of tan, we will take 1 away, and we will be left with tan squared theta. And on the power of 5, we will take 1 sec theta, and we will be left with sec power of 4 theta. And we isolate the tan theta sec theta as our potential derivative. And then we get a statement that looks like this one. Now it is tan squared theta sec to the power of 4 theta after we've isolated the tan theta and sec theta, and we put them next to the theta there. So this statement that I have here, it's exactly the same as what we have there on top. It's just that now the powers are separated. Now, as we have seen, what we have as our f of x is the one that we did our derivative on the right-hand side. So what we need to remain from these two factors, we only want to see sec remaining, not tan anymore, because we are using sec as f of x so that we get the derivative that we are having there on the right side. So which means that we are supposed to look for the identity that can exclude this tan squared and replace it. And the identity is the same that we did, but we just have to make tan squared the subject of the formula. In the previous example, we replaced sec squared by 1 plus tan squared. Then we just transport 1 to the other side, and we are left with tan squared on the left-hand side. So we're going to replace tan squared by this sec squared theta minus 1, so that we get this step. So now you will remember that we have got all these things that are on the right-hand side here that are supposed to be multiplied inside this bracket. So that is the next step now. We are going to have this sec squared multiplied by this sec to the power of 4, and we get sec power 6. And then together with all these values that I said are derivatives. So which means we are going to get that. And then the other one is multiplying by minus 1. That is why the power of 4 remains exactly as it is that you see there, and all the values that you see as the derivatives. Now I've written them in red so that you can see that these are just standing there as derivatives of our function f of x. In this case, our function f of x is sec theta. Power 6 is your n. In the other one, it's sec theta. Power of 4 remains, and you apply that rule number 2, and the answer will look like that. So you add 1 to power 6, and you divide by the result. You add 1 to the power of 4, and you divide by the result. And the final answer is 1 over 7 sec power 7 theta minus 1 over 5 sec power 5 theta plus c. And if there is no question, we are now done with integrals of trigonometric functions. Is there any question? Before we start with integrations of hyperbolic functions. Now, hyperbolic functions, same thing that we talked about with trigonometry. They have got their own identities that are a little bit similar in some places with the ones for trigonometry, but there are some differences. That is why for you to do your replacements of things here, you need to look out for the formulas separate. They are not the same as the ones for trigonometry. So there are some differences here and there that you will see as we go on. But now, as I have said again, I said to do integration, you have to be very, very sharp with your derivatives. Now, if you can remember derivatives of hyperbolic functions, you will remember that the derivative of sin 3x will be 3 cos 3x. And if you can look at this question that we have, so it means that if you can take the whole denominator, 5 plus sin 3x as f of x, finds its derivative. The derivative will be cos of 3x, but it has to be multiplied by the derivative of 3x, which is 3. So here, for us to have the one on top as the derivative of the one at the bottom, we will just need a 3. To include a 3 there, then we are sorted. So when you get two names of hyperbolic functions, you need to think of rule number 2 and rule number 3 first. If there is nothing you can do about, you think about that rule. And in this case, this will be rule number 3. And if you can look at rule number 3, uh, rule number 3 goes like this. It will have the derivative of the function f of x divided by f of x as it is, which I just rewrote here as f of x to the power of minus 1. I'm emphasizing to write it like this so that you can see that you cannot use rule number 2. Because if you try and use rule number 2, you are going to have a situation where you will have minus 1 plus 1 divided by the result. So which means minus 1 plus 1 is that 0. Divide by 0 and dividing by 0 mathematically doesn't work. So this is the rule number 3, which will go and look like that. Is that 1 over 3 that was outside? Remember this 3 here was brought so that this will be completely the derivative of that. Remember the derivative of sin 3x will be 3 cos of 3x. That's why we need this 3 to be sitting here, and we compensated it by 1 over 3 that is out there. And this, what you have here, is exactly the same as what you have there on top. If you multiply the 1 over 3 inside, it cancels this 3. Cos 3x will sit on top. This one, if you bring it down, it's exactly that which we have there. So now it becomes ln of that according to rule number 3. So we go to the next example. Now, the next example is that one. Is the integral of e to the power of 2x cos e to the power of 2x dx. Now, with this one, because it is cos and the cos doesn't have a square, a power or an exponent, it doesn't. So what you do is you go and check an integral in the information sheet that is the integral of cos e to the power of 2x. The reason why I say that is because you will remember that the derivative of e to the power of 2x contains e to the power of 2x. And there is this e to the power of 2x that is outside there. So which means that then the rule will be satisfied if we just include a number that will make the derivative of e to the power of 2x correct, which is the number 2. But say, for example, this was the integral of e to the power of 2x, and it was cos of x, not e to the power of 2x. The number in front there was x. Then it would mean that this is a new question altogether, and that question will need what you call integration by parts. But this is not the kind of question, because the value inside this cos here, it's connected to the derivative of the number that the derivative of the number inside here is directly related to the number that is outside there. So because of that, then it means that this is a direct rule of cos that you go and read inside the information booklet. But then what you just need to do is to find the real derivative of e to the power of 2x. And you'll realize that to find that derivative, you will need to first find the derivative of the exponent, which is 2x, and the derivative is 2, then multiply by e to the power of 2x as it is. So which means that in that integral, we are just missing the 2. And that 2, we bring it inside and we compensate it by a half outside. And now what sits there in red is the derivative of what is inside this cos. And when you go to rule number 19 of your integrals, you will find this rule straightforward, which has got an answer that looks like that. It's half ln sin of e to the power of 2x plus c. The half is the one that we just brought down as it is. The integral is the one that you can read from your information booklet. And that's how easy this question is. But it wouldn't be easy if you do not understand your derivative, because your derivative will direct you to check this inside here, the cos and what is outside. If there's a connection, then you know that it is the straightforward rule. If there is no connection at all, then it means that we have got two functions of x. It will be an x e to the power of x here and a cos of x sitting there, which needs you to come up with now the issue of integration by parts. So that is all about this one. Let's check the next one. Now, as with trigonometrical ratios, the hyperbolic functions will only have integrals of squares of sec squared and cosec squared. Those two will have integrals, straightforward. But sin squared, tan squared, and cos squared, and cos squared, cos squared, they won't have direct integrals, which means if you find the power of 2 like this, you need to go and try and remove the power of 2. How do you do that? You go to hyperbolic identities. They are there in your information sheet, and you will find that there is one that looks like that. It is sin squared x equals half cos 2x minus 1. Now the right-hand side does not have an exponent anymore, so we will replace that sin squared x by the right-hand side, and then we will get something that looks like that. Now, as I've said, the half does not contain x, so we can move it outside if we want. And we are going to look at rule number 17. Rule number 17 will direct us that the cos 2x must be accompanied by the derivative of 2x, which is 2. So that is why now, when we expand these integrals, we have the following that you see here. We have this half that went outside was supposed to be sitting here. Now, because we needed to introduce a 2, so we must counter that 2 by another half. That multiplies the original half to give us the 1 over 4. Now, if you can take this 1 over 4 and multiply it in here, it will get simplified to half, which is the same as that you have there. But this 2, as you can see, it's in red. We need it to sit there for us to be able to go and do the integral of cos 2x. If you go to your information booklet, you will find that the integral is there perfectly sitting like that with a derivative of f of x outside and cos of x dx. Then what you just need to do is to just copy exactly as it is there. The other one is a half integral of 1 dx, which is a straightforward integral of 1 dx, and then you get that as the answer. And we move to the next question. The next question is the integral of sec square root x tan square root of x all over square root of x dx. Now, the same reasoning here applies if you know your derivatives. Then you can see the following, that sec square root of x tan square root of x is the derivative of sec square root of x. Is connected to the derivative of sec square root of x, which means there should be an integral that looks like this. The only thing that we need to just do is to see if this square root of x at the bottom is connected to the derivative of square root of x in some way. Then what we do is go and find the derivative after we have looked at rule number 22. It's rule number 22 that will help us with the integral of this thing that we have there. But we also need to go and first find the derivative of square root of x. And you will know that square root of x is the same as x to the power half. So the derivative thereof is half x to the power of minus half. Now, if you can look at the one at the bottom there in the integral, if you can take it up, it becomes x to the power of minus half. It just misses the half that you see there. So we can bring this half ourselves. Putting a 2 outside and putting the half inside is the same as multiplying by 1. And what you see in red there is the derivative of the square root of x. And you go to rule number 22 and you read the answer from there and you find that the answer is that one. Minus such of square root of x plus c. And that's how simple this question is. But you cannot be able to see this if you don't know your derivatives. Your derivatives are the key for you to be able to do integration very easily. Now going to the next question. And now this next question actually looks like what I've talked about before. That now we've got an e to the power of x and a sin of x dx. Now, under normal circumstances, we should go straight to integration by parts. But luckily, we are dealing with hyperbolic functions. Hyperbolic functions, if you go to the information booklet, you will find that they are having equivalence in exponential form. That's where it assists us to avoid integration by parts. So you go there and you look at the rule that gives you the form of sine x in exponential form. And you find that this is the rule. It's there. You just go there, find it, come and import it, and put it inside your integral, like what I just did there. So you replace the sin of x by its equivalent, which is e to the power x minus e to the power minus x all over 2. And it reduces your integral now into just an integral of an exponential function, which you already have done. It's just a matter of simplifying here. So we factor out the half and we multiply the e to the power of x inside the bracket. And we eventually get half e to the power of 2x. When we multiply e to the power of x by e to the power of x, we have e to the power of x, and then we add the other x, and it becomes 2x. Then we multiply e to the power of x by e to the power of minus x, and it becomes e to the power minus x plus x, which is e to the power of 0. And e to the power of 0 is exactly equal to 1. And that is where we get this minus 1 inside the bracket. Now we go to the rule that will assist us to integrate an exponential form, and it is rule number 4. So, excuse me. So rule number 4 says, to do this integral of an exponential function, the exponential function must be accompanied by the derivative of what is in the exponent. And the derivative of 2x is 2. So which means that the 1 over 2 will be multiplied by another 1 over 2 to compensate for that 2. And we've got our e to the power of x dx minus 1 over 2 integral dx, which is the integral of 1 dx. And we read from number 4, and we do the normal integral on the other one, and we get the answer as 1 over 4 e to the power of 2x minus half x plus c. And going on to the next question. You can also go and try using integration by parts and see if you will be able to reach the same conclusion. Remember, after you do that, if you are using by parts, you may have your answers in terms of what cos x and sin x, and you will remember that those can be written in exponential form to you for you to be able to change it to so that you see that the answers are exactly the same. Next question is this one. Integral of cos power 4 x minus sin power 4x. And also in the same vein as we talked about in trigonometric functions, most of our identities are squares. So with this one, with powers of 4, we can be able to change this into squares by factorizing, because what is in that bracket looks like the difference between two squares. And then when we factorize, we get something that looks like that. Cos squared x plus sin squared x into cos squared x minus sin squared x. And now you can go to your information booklet and check these identities of these hyperbolic functions. You will find one that looks like that. It says cos squared x plus sin squared x is equals to cos 2x. Please do not confuse these identities with identities of trig functions, because in trig functions, you would think that this is equals to 1. But in hyperbolic function is something different, which looks like what you see there. Now, in hyperbolic function, what is equals to 1 is the other bracket, cos squared x minus sin squared x. So that is equals to 1. So we're going to use these two identities to substitute substitute them into the statement on our left hand side there, and what we will get is only integral of cos 2x dx, because the second bracket has been replaced by 1, the first bracket has been replaced by cos 2x. And there's a rule that is straightforward for you to go and find this integral. It's just that that rule is number 17, and when you look at it, it needs a function of 2x to accompany cos 2x, and that is the derivative of 2x, which is 2. That's why now we have to bring on the half and the 2. I put the 2 in red for the same reasons I explained before, because it is just there to accompany cos x for it to do the integral as it's shown in rule number 17, and you find that the answer is half sin of 2x plus c. Right, so we go to the next example, which is the end of our lesson today. So I think I have heard only ladies' voices. Ladies, we are done for today. If you have any questions on these two sections, please do not hesitate to email us. We will be available to assist you at any given time. Thank you so much for attending the lesson today.
Oh, thank you, sir. I wanted to apologize for earlier. My speaker was off and I was looking for my earphones as well, so I couldn't reply. And you had started class already,
Oh, okay.
so
No, that's fine.
okay.
No, thank you so much. And if you've got any questions, I think you've got Dr. Anastasia's email address. You can forward the emails to her. She will be able to forward it to us, and we can be able to do the. And if in actual fact, when you were forwarded the email of this lesson, my email should be there. So
Sorry, sir.
yeah,
What's your email address?
my email address should be in the email that you got there, but I can write it on the chat box here. And this in fact this lesson was recorded, so when you get the link for this, you should be able to get my address there as well.
Okay.
But anyway, even if you send it to Ma'am Anastasia, I will be able to get that email as quickly as possible. It's called Econen, EKONEN at unisa.ac.za. So that's my email address. And unless there is anything, any question, any comments, this will be the end of the lesson. And welcome and goodbye to the guys that I didn't see at the beginning. All right. Bye-bye.
Bye, sir.
All right.